morning, welcome to new lecture. Today I will review several examples. We will solve these problems using slope deflection method. So, in order to solve problem using slope deflection method, first I should find fixed end moment. You can look at the table in different textbook. You can find table for this, but some of those they are very important. It is good if we memorize it. I'm writing those. If we have concentrated load to end fix, the moment at the support is PL over 8, PL over 8. In slope deflection method, I prove it. I use counterclockwise positive, so I will call this positive moment. This is negative moment. In some book, clockwise is positive. You can choose whatever you want. So PL over 8, PL over 8. If we have the same beam, but load it is not at mid-span. The distance of load from here is A, from this side is B, and the magnitude of the load is P. In that case, this support traction will be P A squared B over L squared. This support traction will be P A B squared over L squared. If we have distributed load, and it is uniform distributed load, the intensity of the load is W. In that case, fixed end support W L squared over 12, W L squared over 12, and the length of span is L. If we have distributed load only in half part of the beam, like this, in that case, this will be 5 W L squared over 192. This will be 11 W L squared over 192. And this is L over 2, L over 2. If we have trapezoid shape, something like this, symmetrical one, this part is A, this part is A, and the entire length is L. For this case, support tractions, both they will be equal because of symmetry, and it will be W over 12 L times L cube minus 2 A squared L plus A cube. If we have triangle shape, something like this, this will be W L squared over 30. This will be W L squared over 20. If we have this kind of loading, and you see it is symmetrical, for this case it will be 5 W L squared over 96. Both they should be equal. 5W L squared over 96. For this one, we have only concentrated moment, and you see the distance from the left support is A, from the right support is B. This will be M A over L squared 2B minus A. This will be M B L squared 2A minus B. I think these are enough. Of course, we have more cases. You can look at those tables. These are important ones, and it is good to memorize it. But always you can use table. Let's look at the first example to see how we can approach to this kind of problem and how we can find reactions using the slope deflection method. A continuous beam ABC is carrying uniformly distributed load of 2 kips per feet in addition to a concentrated load of 20 kips. Draw bending moment and shear diagrams for this beam. Let's look at this beam. This is one continuous beam. This part is 4 feet. This part is 6 feet, 3 feet, 3 feet. Entire this span is 6 feet. Point A, B, C. Distributed load here is 2 kips per feet. At mid span, here we have 20 kips load. At BC part we have another distributed load, uniform distributed load, and the intensity of this one it is 4 kips per feet. We want to find reactions, shear diagram and moment diagram. First step, we should find degree of freedom. In order to find degree of freedom, we will look at the node A, B, C. Each node can rotate, but node A and C, because they are fixed support, rotation is known, it is 0. So the only rotational degree of freedom we have here, it is rotation theta B. It is only theta B. If we convert all these support or node to the pure hinge, there is no lateral deformation. So translational degree of freedom is equal to 0. Altogether, degree of freedom for this system is only 1. If I imagine, visualize the deformed shape of this beam, it will be something like this. Roughly something like this. So you see the theta B here, it is unknown. Let's look at first 2 different spans we have here. Span AB and BC. Fixed end moment for AB will be equal to reaction will be counterclockwise, so positive. If I assume this AB it is both end fixed, it will be W to L squared, 6 squared over 12. Because we have concentrated load as well, P times L over 8 plus P, it is 20, times L, 6 over 8. That will be equal to 21 kips feet. So fixed end moment for AB span, MAB in this side will be counterclockwise, so positive I find. For BA, the magnitude will be the same, but the direction here, the resistant reaction moment will be it will be clockwise. Look at here, this one is counterclockwise, this one reaction is clockwise, so it is negative. I will write that magnitude should be the same, only negative 21 kips feet. For span BC, again the same thing, FBC. This side it is counterclockwise, positive W for L squared over 12. It will be 5.33 kips feet. For M fixed CB will be equal to CB side clockwise negative, everything else is the same, negative 5.33 kips feet. So I find M fixed. I find all these M fixed. So write these down. I will continue because I don't have enough space. I should remove these. Now I will write the slope deflection equation. Slope deflection equation MAB will be equal to M fixed AB, which I find it plus 2EI over L, L here is 6, times 2 theta A plus theta B. Theta A is equal to 0 because it is fixed support here. So MAB will be equal to 21 plus 2EI over 6 times theta B. MBA will be equal to M fixed BA plus 2EI over L 2 theta B plus theta A. Again theta A is equal to 0, so MBA will be M fixed BA, it is negative 21 plus 2EI over L, it is 6 times 2 theta B. So 2 times 2 here, we can write even 4 here. MBC will be equal to M fixed BC plus 2EI L for this span, which is 4, times 2 theta B plus theta C. Theta C again it is 0 because this is fixed support. We know theta C is equal to 0, that will be equal to M fixed BC 5.33 plus EI theta B. And CB will be M fixed CB plus 2EI over 4 times 2 theta C plus theta B. Again theta C is equal to 0, So the answer for this will be negative 5.33 plus half EI theta B. After I wrote slope deflection equations, I should look at to the degree of freedom I have here, theta B, and over there, what is the equilibrium equation? Let's get to the equilibrium equation. Equilibrium equation, if I show free body diagram over there, this is B. If I cut it, I will have what? I will have two moments, and the summation of these two moments should be equal to 0. So MBA, MBC. The summation of these two moments should be equal to 0 in order to keep this joint in equilibrium. So I will write that. I will write MBA plus MBC is equal to 0. In any rigid joint, you have the summation of moment for all members reached to that rigid joint should be equal to 0. Always you should apply this for any rigid joint. This is rigid joint because it is continuous member. Rigid joint, the summation of moments in the end of all members reached to that joint should be equal to 0. MBA, we find it, but it was negative 21 plus 4EI over 6 theta B plus 5.33 plus EI theta B is equal to 0. From here I can write 1.66 theta B EI is equal to 15.66. From there I can find theta B is equal to 9.4 over EI. After I found theta B, I can plug this theta B in slope deflection equations one by one, so I can find MAB, MBA, MBC, MCB. Let's do that. Now I have theta B magnitude. If I plug that in slope deflection equations, I will find MAB is equal to 21 plus EI over 2EI over 6 or EI over 3 times theta B will be 9.4 over EI. That will be EI and EI, they will cancel each other, 24.14 cubes feet. MBA will be equal to negative 21 plus EI over 3 times 2 theta B times 2 times 9.4 over EI. That will be equal to negative 14.73 cubes feet. MBC will be 5.33 plus 9.4 EI times EI. That will be 14.73 cubes feet. MCB will be minus 5.33 plus 9.4 over EI times EI over 2. That will be equal to negative 0.63 cubes feet. So I found all reactions, moment reactions. Now I can draw free body diagram for all segments and I write equilibrium equations. I satisfy equilibrium equations and I find the reaction, force reaction. Let's do that. Now I have magnitude of moment reaction for AB, BA, BC, CB. After that, I can look at the each span one by one. For AB, if I draw free body diagram, I have external load, which is distributed load. The intensity of load, which is 2 kips per feet. I have concentrated load at mid-span, that is 20 kips. I have moment reaction MAB. I find it, that was 24.13 kips feet. In this side, I have moment reaction MBA. I find that because it was negative, which means clockwise, 14.73 kips feet. And I know this span is 3 feet, 3 feet. I have here the reaction, force reaction VA. Here I have force reaction VB at, let's call it left side, VBL. So I cut this part only. Now if I take moment respect to B point, I can find VA, because negative VA times 6 minus 14.73 plus 20 times 3 plus VA times 6, let's see, VA times 6 clockwise negative, minus 14.73 clockwise negative, plus 20 times 3 plus 2 times 6 times 3 for this distributed load respect to the B, plus 24.13 is equal to 0. From there you can find VA is equal 17.56 kips, and it will be upward. Summation of forces in vertical direction is equal to 0. That means VA, which we have it, plus VB left minus 2 times 6 minus 20 is equal to 0. You will plug this here and you will find VB left. This is VB left, means at left side of the point B. You can find that is 14.4 kips. I can do similar things for this span BC. So I will cut that. I will draw free body diagram for that part. If I do that, I will have four kips per feet. This is 0.63. It was negative, so clockwise, positive 14.73, so counterclockwise. This span is 4. You have external load. What else? You will find here VB right and VC. Now, if I take moment respect to the C, what I have VB right negative times 4 minus 0.63 plus 4 times 4 times 2 minus 14.73 is equal to 0. From there you can take this to other side and you will find VB right is equal to 11.52. VB right plus VB left will be entire reaction here. So you should add that, and if you write summation of force in vertical direction, you can write VB right plus VC minus 4 times 4 is equal to 0. From here you can find VC is equal to 4.47 kips. So you find moment reaction at point A, MAB, force reaction at point A, VA. You find moment reaction at BA, force reaction here, B left and right. If you add left and right, it will be one reaction here. And you have now force reaction here and moment reaction at point C as well. So we find all moments and force reaction, shears. So I can draw shear diagram and moment diagram. Shear diagram. As much as reaction, I will move up the reaction at point A. VA it was 17.56. From left to right there is a distributed load. So with constant slope I will move down. 20 I will move down. There is continuous load with constant slope I will move down. VB left and right you will add, so you will have reaction RB here. As much as reaction RB you will move up. If you move up there, this will be 14.33. This side will be 11.52. Then let's see. Then with constant slope again you will move down, and with VC here you will close diagram, which is that is 4.47. Positive, positive, negative, negative. Okay, let's now look at moment diagram. MAB, it is counterclockwise here, but that if you take with rand point A and rotate in this direction, that will produce compression underneath of the beam. It means negative moment. So MAB here in moment diagram it is negative, negative 24.13. Distributed load means it is, the shape is curve shape and parabolic shape. So it will come here. If you cut just before load 20 and find internal moment, or if you find area underneath of the shear diagram, you will reach the positive moment of 19.4. So you can cut just before this load and find this end, that will be 19.4, and it will be in this direction, that is producing tension in dashed line. At point B, MBA was 14.73. That will be again negative because it is in this direction, and if you rotate in this direction, compression underneath of the beam, and from here to here it is distributed load, so it should be curve shape, something like this. Then we have moment at C, which is in this direction. if you rotate point C, you take with rams and rotate in this moment direction, you see it create compression underneath of the beam. It is negative. The reaction here was 0.63, and again distributed load, so curve shape, and the maximum should be here. So it will go to positive convex like this. You can find this magnitude because you can find where it is 0. In the shear, because derivative of moment is shear, so any place is shear force is 0, we will have maximum moment. Okay, thank you so much for watching this lecture. See you next session. Bye bye.